We're going to take a look at number 44 on page 451 from the handout yesterday. Number 44, thank you. We're looking at inverse tan of tangent of negative 2 pi over 3, right? And so the thing about tangent that we know is that it returns values between negative pi over 2 and pi over 2. So even though these are inverse, these happen to be inverse of each other, because this is outside of the range of inverse tan, it's not actually going to, the composition rule is not going to work perfectly in this case. What it is going to do is it's going to spit out tan inverse when you take of tan negative 2 pi over 3 is going to spit out an angle that has the same reference angle as negative 2 pi over 3, and that is also, I'm going to give the same value for tan in terms of the sign, but it will be between negative pi over 2 and pi over 2. So if you think about negative 2 pi over 3, that's just outside of that range, right? It's negative 2 pi over 3. And so we end up having a reference angle here of pi over 3. So we need an angle, and in the third quadrant here, tangent is negative, right? It's positive. Tangent is positive in the third quadrant. And so we need an angle that has a reference angle of pi over 3 and that is in the first quadrant, right? It has to have the same reference angle and have the same sign for tangent. So it's got to, inverse tan once again can give me an angle between negative pi over 2 and pi over 2. So an angle that has a reference angle of pi over 3, there's only two choices, pi over 3 and negative pi over 3, right? Negative pi over 3 though is going to give you a negative value for tangent, and positive pi over 3 will give you a positive value for tangent. So the one you want is positive pi over 3 in the first quadrant, where it's going to give you a positive value for tangent. And so this whole thing is going to end up equaling pi over 3. Just because of the range of inverse tan. So the composition rules for these inverse functions only work over their natural range. And otherwise you have to go through this process to determine what the value actually ends up being. Other questions from the homework? Today we're going to begin talking about trigonometric identities. All right, so trigonometric identities. First of all, what's an identity? So an identity is anytime we have one function equals another function, right? Generally speaking. We have an identity if one function f of x equals another function g of x. Another way we could refer to this is and this is for all x, sorry. Right, so essentially, another way of saying that is the solution is an equation whose solution set is all real numbers, right? We would say these are identically equal. So an identity is another, and so in layman's terms, once again, and the way I like to think about it, because it's a little more straightforward, is just to say that an identity is an equation whose solution is all real numbers. So a basic example of an identity would be x plus 1 squared, right, is equal to x squared plus 2x plus 1, right? That is always true no matter what value x happens to be. So if someone just gave you this equation and said solve it, you'd end up coming up with the fact that all real numbers is the solution, right? So that is an example of an identity. Anytime the left side of the equation always equals the right side of the equation, regardless of what the variable might be, right? Whereas other equations that have only one or two solutions, right, are not identities. You know, an example of an equation that's not an identity is the equation 2x plus 3 is equal to 5, right? We end up getting x equals 1, right? That's not an identity. Right, so not all equations are identities, just ones that have solutions that are, whose solution set is all real numbers, okay? So, from a trigonometric perspective, not identities would be like sine x equals 0. That's not always true, right? That might be true. This is true if what? If x equals, what's a value of x that'll give me 0 for sine? Pi over 2, 3 pi over 2, 5 pi over 2, any odd multiple of pi over 2, right? So that's what we call a conditional equation. It's not always true. Not an identity. So that is not an identity. Another example of a conditional equation that would not be an identity is sine x equals cosine x, right? That's true sometimes. Can we think of an angle where sine and cosine are the same? What's one possible solution? Where do they both have the same value? Pi over 4, yeah, 45 degrees. Pi over 4 is 1, and then they have the same value again in the third quadrant with an angle of pi over 4, right? So that's going to be 5 pi over 4, right? And then again, 9 pi over 4, right? And so forth, right? So every pi over 4, and then every 4 beyond that. But once again, not an identity. It's a conditional equation. So these are trigonometric equations that are not identities. So it's important to realize that not all trigonometric equations are identities, and not all are conditional equations. There's a combination of both. So we've actually had some experience with the identities so far, that we have so far. The identities that we know, so these are the basic trig identities that we're going to be working with today. We're not going to worry about any new identities yet. We're just going to work with the ones that we have. But the basic trig identities are the quotient identities. Tan theta equals sine theta over cosine theta. We have cotan theta equals cosine theta over sine theta. We have secant theta equals 1 over cosine theta. We had cosecant theta equals 1 over sine theta. We had the Pythagorean identities from the other day. Sine squared theta plus cosine squared theta equals 1. Tan squared theta plus 1 equals secant squared theta. And then cotangent squared theta plus 1 equals cosecant squared theta. And then the last ones are the even odd identities. Sine is an odd function, so sine negative theta equals negative sine theta. Cosine is even, so cosine negative theta equals cosine theta. Tangent is odd. Tangent negative theta equals negative tan theta. Secant is the reciprocal of cosine, so it's also even, just like cosine. Cosecant is the reciprocal of sine, so it is also odd. Whoops. So negative cos. Whoops. And then cotangent is also odd, just like tangents. negative cotan theta. Oops. All right, so these are all of the identities that, that we have seen so far. All right, and they all have, I didn't put the names here, but they all have names. These first ones, these are the quotient identities. I missed one of the reciprocal identities. Cotan theta is 1 over tan theta. So these are the quotient identities, these are the reciprocal identities, these are my Pythagorean identities, and these are my even-odd identities, right? So quotient identities, reciprocal identities, Pythagorean identities, and then the even-odd identities, right? So these are all the basic identities. We proved those all in the previous sections, and those are the only ones that we're going to be working with today. Okay, and so the whole point, what we're going to be doing with these identities today is we're going to be manipulating algebraic expressions and simplifying algebraic expressions and a little bit establishing identities by using these identities. One thing that these identities allow us to do is to simplify trigonometric expressions. So if I asked you to simplify the expression cotangent theta over cosecant theta by rewriting entirely in terms of sine and cosine. Rewriting and reducing in terms of sine and cosine. Okay, so that means we want to take this expression here, which I butchered, and get it entirely in terms of sine and cosine, and then reduce that as much as possible. Okay, so why don't you go ahead and mess around with that. Use the identities that we've established so far, and try and manipulate that expression by doing algebraic substitutions using your trigonometric identities to get that entirely in terms of sine and cosine. A lot of this today is just going to be like puzzle solving. We're going to be using the trig identities that we have to sort of manipulate these expressions. Okay, so to do this, when we're just trying to get everything in terms of sine and cosine, one of the easiest ways to do that is just to use the quotient identities and the reciprocal identities. So looking at this expression right here, cotangent we know is just, so we start off with this, cotan theta over cosecant theta. Right, and we know that cotangent is just equal to cosine over sine. Right, so that's entirely in terms of cosine and sine, and cosecant is just 1 over sine theta, right? And so this is the same as multiplying by sine theta, right? And so what happens then? The sine thetas cancel, and we're left with just regular old cosine theta. So that's a much simpler way of saying cotangent theta over cosecant theta. So by using the identities, we've simplified that expression by a great deal. And so that's one of the strategies we can use for simplifying a trigonometric expression, is to just get everything in terms of sine and cosine. That's sort of our first go-to in a lot of cases. But sometimes we need to use some other methods as well. So another example would be and I want to simplify it. Let's say I have the expression 1 plus sine of u over sine u plus cosine u, cotangent u minus cosine u all over cosine u. Right. Another strategy we can use for simplifying is if we have two fractions that are being added together, one thing we can do is give them a common denominator and combine them into one fraction. So what would the LCD of these two be? If I wanted to...
Sine u and cosine u?
Yeah, sine u, cosine u. So this one's going to have to get multiplied by cosine u. right? And the other one's going to have to get multiplied by sine u. Right, and that's all going to end up being over sine u cosine u. And now it's just a matter of going through and doing some simplification. We notice at this point everything is in terms of sine and cosine except for this cotangent right here. And so we're going to bring to bear that other strategy too. Let's go ahead and get this cotangent entirely in terms of sine and cosine, write it as cosine over sine, which is going to be convenient in a second here. But I'm going to go ahead and distribute in the numerator here. I'll get cosine u plus cosine u sine u. And then plus sine u times cosine over sine. Whoops, and then minus sine u cosine u. Ran out of room there. All right, all over sine u cosine u. And now we're going to see that these are going to cancel, right? And over here, the sine u's will cancel, right? And so we'll end up just getting, we'll have cosine u plus cosine u on top, which is just 2 cosine u over sine u cosine u, right? And then we can just cancel the cosines, and we'll be left with 2 over sine u. And if we wanted to write that, you know, we could keep it entirely in terms of sine and cosine by just leaving it as 2 over sine u, but I could also call that 2 cosecant u if I didn't want to have a fraction in there. Either or, it all depends on how you want the answer. But once again, we've taken this very complicated looking trigonometric expression, we've reduced it down to 2 cosecant u, or 2 over sine u. And so sometimes we have to get a little bit creative with our algebraic methods and just sort of try stuff out. In this case, combining it into a single fraction. Sometimes that's the right way to go. Other times, maybe not. But a lot of times it works pretty well. Or it can be a strategy that you can use. So you're going to have to, just like finding your way through a maze, try a bunch of different stuff, right? And let's look at another one that involves another. So if I'm asked to simplify sine squared x minus 1 over tan x sine x minus tan x. So what you might notice about the numerator and the denominator is that they're both factorable, right? And so sometimes factoring comes into play. Just like, especially if we have a fraction, you know, with algebraic fractions, we factor and simplify. Well, in this case, we can also factor and simplify. Sine squared x minus 1, what is that? What factoring structure does that have? Sine, what?
Sine x plus 1 and sine x minus 1.
Yeah, it's a difference of squares, so it'll factor as sine x minus 1 times sine x plus 1. And on bottom, what can we do for factoring?
Just take out the tangent.
Take out the tangent. And we're left with sine x minus 1. And so by factoring the top and the bottom, we can now go ahead and cancel the sine x minus 1s. And we'll just be left with sine x plus 1 over tan x, which at that point, there's not much we can do with it. Even if we put tan x in terms of sine over cosine, it wouldn't really help us all that much. So at that point, we can sort of just leave it like that. All right, so in addition to do what's called establishing or verifying identities. Right? Because we do need to, some identities, you know, are not part of the basic identities we just established, but they're still true, and we would like to be able to prove that they are true. So for instance, what if I had the identity cosecant theta times tan theta equals secant theta, right? So I'm giving you, instead of just an expression to simplify, I'm now giving you an equation, and I'm saying it's an identity, and I want you to show me that that actually is true. So prove to me that this is always true no matter what theta is. Prove the identity. All right, and so what you need to do is you need to use your trigonometric identities to break this down to a statement that we know to be true no matter what. Right now, looking at this, I don't know necessarily off the top of my head that cosecant theta times tan theta equals secant theta. But if I can get this down to a situation where the left side is exactly like the right side, then I've proven it, right? So I want to end up having the same thing on the left side that I have on the right side. So my hint for this one is just get everything in terms of sine and cosine and simplify and see what happens. And only work one side of the equation. Pick one side and work it. Don't try and work both sides of the equation at once, okay? Okay, so looking at this one right here, I'm just going to work the left side, right? And so what I'm going to try and do is try and make the left side look like the right side. So if I can get this to become secant on the left side here, then I've proven this identity, because obviously secant equals itself. And once again, the strategy for this is just to work one side of the equation. Do not try and work both sides of the equation at the same time. So pick a side and work that side. So let's go ahead here. Cosecant is 1 over sine, and tangent is sine over cosine. Right. And so the sines cancel. We're left with 1 over cosine theta, right? And we know that that's equal to secant theta. So at this point, right, we have proven that identity. That was supposed to be a check mark. Right, identity proven by showing that the left side can be turned into the right side. And just work the side that you can, that seems easier for you to work. Don't try and get, don't get too concerned about like which side. Just pick the side that, you know, you can see the best and that works out for you the easiest. Okay, let's look at another one. What about the identity? Say, prove the identity or establish the identity that sine squared of negative theta plus cosine squared negative theta equals 1. And once again, only work one side of the equation and bring to bear the trigonometric identities that you know. The first thing I would do here is go ahead and realize this is just sine of negative theta squared, right? That's just what that notation means. And this is cosine negative theta squared. So I'm just going to work the left side of the equation here. So sine negative theta is equal to negative sine theta. All right. And cosine negative theta is just equal to cosine theta. So we end up with cosine squared theta there. And then squaring negative sine is just going to be positive, right? Sine squared. And that's our Pythagorean identity, so we know that that equals 1. And so now we've shown that the left side and the right side can be made into the same thing. So once again, work only one side of the equation when you're proving these identities right here. All right, let's just keep on doing some more here. All right, for the next one, go ahead and prove or verify the following identity that sine squared negative theta minus cosine squared negative theta all over sine negative theta minus cosine negative theta. Show that that equals cosine theta minus sine theta. All right, give that a shot. All right, so let's take a look at this here really quickly. I'm going to start with the left side, and in general, a tip is to start with the side that is more complicated, that there's more stuff going on. So in this case, I would start with this side and try and start with the side that's more complicated and then just break it down and simplify it, right? Because it's usually a lot easier to simplify than it is to expand, right? So instead of starting with this side and trying to expand it out to look like this side, start with this side and try and simplify it down to this side, right? So I'm going to start with the left side here, and sine squared of negative theta, we know just like we did before, that's going to end up being just sine squared theta, because even though sine of negative theta is negative sine theta, when I square it, it's going to become positive. And the same thing is going to be true for cosine squared theta, although cosine of negative theta is just cosine theta itself anyway. So that negative there doesn't really matter. And the bottom here, though, on the other hand, we're going to end up getting negative sine theta, right, minus cosine theta after we apply the even odd identities. And so on top, we have a difference of squares, so let's go ahead and factor that. We end up getting sine theta minus cosine theta times sine theta plus cosine theta. And on bottom, we see that if I take out a negative here, right, I get sine theta plus cosine theta. And then those factors will cancel, but I'll have a negative on bottom still, so we'll end up with, if I change the sign of both those, I'll have cosine theta minus sine theta. So I've ended up with what I had on the right side of the equation, so I've accomplished my goal, right? So one of the big hints I'm going to give, or one of the big strategies, or let's say guideline, always work with the more complicated side of the identity. Okay, it's a basic guideline right there. All right, let's just keep looking at some more. Something to take a shot at is the following. Sine theta over 1 plus cosine theta plus 1 plus cosine theta over sine theta equals 2 cosecant theta. So go ahead and prove this one. Like I said, I'd start with the more complicated side. And remember some of the strategies we use when simplifying. So take the more complicated side and simplify it. Remember how we simplified expressions like that when we were adding two fractions together from earlier in this section. So we're definitely going to pick the more complicated side, which is the left side again. We're going to try and take this and simplify this down to the point where it becomes 2 cosecant theta. That's the goal here. So the first thing I'm going to do, anytime I have two algebraic expressions that are fractions that are being added or subtracted from each other, I want to combine them into one algebraic expression. So that's the first thing I'm going to do here. I'm going to go ahead and multiply the top and the bottom of the one on the left side by, well, what the LCD, of course, is going to be 1 plus cosine times sine, right? So this one needs a sine. So if I multiply the top and the bottom by sine, I get, let's see this in blue, I get sine squared theta over sine theta plus sine theta cosine theta. Actually, I'm going to keep that factored. So sine theta times 1 plus cosine theta. Okay, and then over here, I'm going to multiply the top and the bottom by 1 plus cosine theta. So I'm going to end up with 1 plus cosine theta squared over sine theta 1 plus cosine theta. And for now, I'm going to keep the bottom of that other one factored. So if I go ahead and I add this together into 1, I'm also going to multiply out the 1 plus cosine theta. And I'll end up with sine theta times 1 plus cosine theta on bottom there. If I multiply this out, I will get cosine squared theta plus 2 cosine theta plus 1. And sine squared theta plus sine squared theta plus cosine squared theta equals what? That equals 1, right? So end up getting 1 plus 2 cosine theta plus 1. Continue to keep the bottom factored. Now on top there, we can add those two together. We get 2 plus 2 cosine theta over sine theta, 1 plus cosine theta. And then at that point, we can factor out the 2, right? And then, miraculously, the 1 plus cosine thetas cancel. And we're left with 2 over sine theta, which is the same as 2 cosecant theta. And so we have what we started with on the left side of the equation. And so we've verified the identity at this point. So the trick there is anytime you have algebraic expressions, so the hint is always to combine algebraic fractions when simplifying. Okay. All right, let's take a look at another one. Got to get a lot of practice at these because they're tricky and there's no like formulaic way of doing them. It's a matter of messing around and applying the algebraic strategies and trig identities that you know and hoping that you can get there. Tan x plus cotan x all over secant x cosecant x equals 1. So you can probably guess which side it makes sense to start with and simplify down. So why don't you guys go ahead and take a shot at that. So I'm going to go ahead, and the strategy that I'm going to use is to start off, I'm going to get everything in terms of sine and cosine. Anytime I see a lot of tans and cotangents, secants and cosecants, in a situation where I can't immediately apply like one of the Pythagorean identities that involve those, then I usually go ahead and write them all in terms of sine and cosine. So we get sine x over cosine x plus cosine x over sine x, right? And on bottom here, secant x cosecant x the same as 1 over cosine x sine x, right? And so then what I'm going to do is I'm actually going to go ahead and multiply by the reciprocal, right? So instead of dividing by this, I'm going to multiply by the reciprocal of this. And so I will get sine x over cosine x times cosine x sine x plus cosine x over sine x times that as well. And we see what's going to happen here is the cosine x's cancel, and then we're left with sine x times sine x. The sine x's cancel, and we're left with cosine x times cosine x. I'm just going to bring this up here. And so this will end up equaling sine squared x plus cosine squared x, which by the Pythagorean identity is just equal to 1. And so at that point, we've got it. We've proven the identity there. Okay. And a lot of times if you see that you're trying to get this to become 1, right, you're taking this and you're simplifying this down so it becomes 1, you might think at some point I'm probably going to see the Pythagorean identity, right, because since that gives me 1. There's other ways, of course, of getting 1, but the Pythagorean identity is definitely one of those ways that comes up a lot. All right, right back at it. Let's go for another identity here and establish it. You guys are going to be identity establishing machines by the time we're done here. So this next one, 1 minus sine theta over cosine theta equals cosine theta over 1 plus sine theta. And I'm going to give you guys a hint because this one's a tricky one. And that is to multiply the numerator and denominator of one of those by the by the conjugate, or just by, I'll just say by a conjugate. You can decide which conjugate you want to multiply by. Okay, so multiplying by a conjugate. Give that a shot. All right, let's give this one a try. We're going to start at the left side, and I'm going to take my own advice here and multiply by the conjugate of the top. What's the conjugate of 1 minus sine theta?
1 plus sine theta.
Okay, and so if I multiply across the top there, I'm going to get 1 minus sine squared theta, right? Whoa, 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 whoa. What you doing? And on bottom, I will get cosine theta times 1 plus sine theta, right? Now, what does 1 minus sine squared theta equal?
Sine squared.
It does, right? Because we know that we're going to have to take the Pythagorean identity, which says that cosine squared theta plus sine squared theta equals 1. So that means that cosine squared theta equals 1 minus sine squared theta. Right, so we got to use that fact there. So we'll get cosine squared theta over cosine theta times 1 plus sine theta. And one of the cosines will cancel, leaving me with cosine theta over 1 plus sine theta. And voila, we have what we started with. So we have verified the identity. Oops. So your homework is here. It's all from a handout I will be sending out today. In addition, just a reminder that there will be no class. No class Wednesday through Friday this week. The next class will not be until next Monday, and we have 2 weeks remaining when we come back on Monday. All right, have a great day, everyone.